Hello everyone, welcome to the engineering chalkboard. Today I'm going to take you through the influence diagram or the ILD for simply supported beam with the UDL longer than the span. So a simply supported beam has a span of 16 meters and is subjected to a UDL load of 13 kilonewton meter per meter longer than the span. Draw the influence line diagram, the ILD, for the shear force and the bending moment at a section 4 meter from the left end or from the left support A. Use the diagrams to determine the maximum shear force and maximum bending moment at this section. We have our loading here, which is the UDL longer than the span. Our span is 16 meters, which is a simply supported beam, and we have placed our load, our point C, 4 meters from the left. So 4 meters from the left to have our point C, where we are going to determine our maximum shear force and the bending moment. And to start off, the maximum bending moment or the maximum positive shear force occurs when the tail of UDL is at C. We're going to start with the maximum shear force, and to determine it, we are going to do the maximum shear the maximum positive shear force and the maximum negative shear force. So at one the maximum shear force occurs when the tail of UDL is at C, and we are going to draw our our beam here. This being point A or support A here, not here, and B, and our point C, we locate it to be somewhere here at 4 meters there. So 4 minus 16, we have 12 here in this side for 12 meters. And so for our maximum positive shear force will occur when the tail of the UDL is at C. So the tail, this is the tail here, and this is the head. So at the start of our UDL is where we are going to place, our load. So at point C. So our loading will start from here. And because it is larger than the span, it is going to extend to a place somewhere there, which is 13 kilonewton per meter. So drop down, extend the supports so that we can draw our influence line diagrams to determine the shear force, the maximum shear force, positive and the negative. So, and our point C, and our beam, let's say it is going to be somewhere here. Yes. In influence line diagrams, to calculate so that we can able to draw our influence line diagram. First, we are going to calculate the ordinates at our point C, where our loading is going to affect our beam. So the ordinate for maximum shear force, SF, to calculate our ordinate, so this is the formula. It is going to be L minus X all over L. So L equals to 16, and our X is the distance from the left support, which is 4 meters. So it is 16 minus 4 all over 16, which is 12 all over 16, and which gives us 0.75. So our maximum for our positive, it is the ordinate for maximum positive shear force. So let's say it's going to be somewhere 0.75 here. And to calculate the maximum negative shear force, the ordinate formula is going to ordinate for maximum negative shear force equals to X all over L. So X is 4 and L is 16. So it is not about division. It is 4 all over 16, which gives us 0.25. Here we are working with decimals to make our work easy. It is going to, let's locate here. Let's locate it here to at this place at negative 0.25. So and our drawings, to draw it, so this is the drawing that you should have at the end. This is the drawing, and this one. The maximum negative shear force occurs when the head of the UDL is at C. So to elaborate this further, this is, as I told you, this is the start and the end. To find the maximum negative shear force, the head should start at C, so that according to this diagram that we have, the negative sign, the negative part of the negative part in the negative shear force diagram, the ILD for the negative shear force is at this side. And because the span of our UDL is large, we are going to place the head, which is the end, at point C to extend backwards. You're going to see it's going to be like this, and so it is going to extend on the further left. So this is point A and point B. Let's extend our lines so that we can draw our influence line diagrams. Hope you can see clearly. This is how our drawing is going to look like. And so we found out that our ordinate was 0.75 for our maximum and 0.25 for our negative shear force. Yes, and this is how we're going to see. So it's supposed to look like. So this is the area that we are supposed to work on, and this is the maximum. This is the maximum negative shear force that we should calculate using this triangle here. I shaded it. So it is going to look like this. And so we have the base and we have the height. And thus, to calculate our maximum negative shear force, it is our area, it is the formula is load multiplied by the area of RLD. This is the maximum negative shear force equals to this, which is 13 kilonewton per meter multiplied by a half multiplied by the base, which is 4 multiplied by 0.25. Sorry by the so and when you calculate all of this, our shear force, our maximum negative shear force is going to be 6.5 kilonewton. And this is the maximum negative shear force at this specific point. So to calculate our maximum bending moment, or for our maximum bending moment, we're going to take our beam like this. I hope you are noting everything down, that for us to get the maximum bending moment, our UDL, it is going to cover the whole span. And we have our point C here. This is A, this is point B. So let's extend the lines down. Not that much, because this is our only last drawing that we are having. So it's going to be like this. And the ordinate, so that you can know where our triangle, our area is going to start, so that we can have at point C where our maximum bending moment is acting. This is the maximum bending moment. So the ordinate for maximum bending moment is equals to x into L minus x all over L. So x is the 4 meters and L equals to the span of the beam, which is 16 meters. So it is going to be 4 into 16 minus 4 all over 16. So it is 4 into 12 to 16, which is going to give us 3. So this is our ordinate, and we are going to locate it at point C. This is where we're going to locate our point 3 at there. It is going to have a triangular look. This is all positive. I'll shade it because this is the area that we are looking for. So our maximum bending moment equals to load multiplied by the area of the triangle, or ILD diagram, which is our loading, which our UDL was 13 kilonewton per meter. So our load equals to 13 kilonewton per meter multiplied by the area, and this is a half multiplied by 3 multiplied by 16. And when you do all of this and inputting it in your calculator, our answer is 312 kilonewton per meter. Not kilonewton per meter, I'm sorry. It is kilonewton meters. So your SI units are very critical, and I believe that you have all enjoyed. You have come to the end of our lecture today. Thank you.